Have you ever wondered what keeps your electronic devices running smoothly, delivering a steady power signal even when the source is alternating current? It is often a tiny but mighty component responsible for smoothing out those power fluctuations, ensuring everything works perfectly. To accurately calculate the capacitor size needed for reducing ripple voltage in a rectified power supply, you primarily use a formula that relates the load current, the desired peak-to-peak ripple voltage, and the ripple frequency. The fundamental relationship is that capacitance is approximately equal to the direct current load current divided by the product of the ripple frequency and the allowed peak-to-peak ripple voltage. The core mechanism behind this calculation lies in how a filter capacitor stores and releases electrical charge. After an alternating current signal is converted to pulsating direct current by a rectifier, the capacitor acts as a temporary energy reservoir. It charges rapidly during the peaks of the pulsating direct current waveform and then slowly discharges into the load during the troughs. This continuous charge and discharge cycle reduces the voltage fluctuations, or ripple. The larger the capacitor, the more charge it can store, and the longer it can maintain a stable voltage as it discharges into the load, thereby minimizing the ripple voltage. The ripple frequency is crucial because it dictates how quickly the capacitor needs to recharge, with full wave rectification typically doubling the line frequency and therefore making ripple easier to manage. To apply this effectively, first determine the average direct current load current that your circuit will draw. Next, establish the maximum acceptable peak-to-peak ripple voltage your application can tolerate. Finally, identify the ripple frequency, which for a full wave rectified 60 Hz alternating current source will typically be 120 Hz. Then, use the formula. Capacitance in farads equals the load current in amperes, divided by the result of multiplying the ripple frequency in Hz by the desired peak-to-peak ripple voltage in volts. It is also important to consider that real-world capacitors possess an internal characteristic known as equivalent series resistance, or ESR. While the primary formula guides capacitance value, a capacitor with high ESR can inadvertently reduce its effectiveness in filtering ripple, especially at higher switching frequencies. This can lead to increased power dissipation within the capacitor and a larger actual ripple than calculated. Therefore, selecting components with appropriately low ESR for power supply filtering is a vital, often overlooked aspect of robust design. By systematically assessing your load current, defining your acceptable ripple tolerance, and accounting for the operating frequency, you can precisely determine the ideal filter capacitor size. This meticulous selection is paramount for ensuring a highly stable direct current power supply, which in turn guarantees the reliable and extended operation of sensitive electronic devices, safeguarding against performance degradation and premature component failure.